In this video, we will present our work for Humanoids 2020, Multi-Fidelity Receding Horizon Planning for Multi-Contact Locomotion. To motivate our work, let us consider how humans traverse uneven terrain. When facing challenging terrain with arbitrary surfaces, humans usually decide the best location and timing of their current step, based on their prediction of future steps. Likewise, when planning multi-contact locomotion in a receding horizon fashion, predicting a few steps ahead is necessary to guide the immediate actions, especially when the terrain has non-coplanar surfaces. However, this usually gives rise to a high-dimensional and nonlinear problem, which is challenging for online computation. Indeed, when synthesizing multi-contact motions, the complexity of the dynamics model has a large impact on the computation time. For instance, although impressive multi-contact motions can be generated by using the whole-body dynamics model, the computation time is usually far from the requirement for online usage, unless contact timings and locations are fixed. This is because the whole-body model considers the mass and inertia of every link, which results in high dimensionality and nonlinearity. Recently, the centroidal model has become popular for multi-contact motion planning. This model is low-dimensional as it only considers the dynamics of the total linear and angular momenta expressed at the center of mass. Unfortunately, the centroidal model is still non-convex, which makes online computation challenging. To improve the computation efficiency, convex approximations of the centroidal model are introduced. However, this comes with the cost of having limiting assumptions or reduced model accuracy. To give more detail, conservative approach explores solutions based on a convex inner approximation of the centroidal model. Despite the fast computation, conservative approach usually requires pre-defined contact locations or timings, which limits its flexibility. Another approach is to rely on convex relaxations. However, this approach may generate unrealistic motions with significant violations on angular dynamics, unless customized solvers are implemented to iteratively tighten the model mismatch. In summary, the existing approaches commonly employ a single dynamics model over the entire look-ahead horizon, and trade off between model accuracy and computation efficiency. When it comes to generating complex multi-contact behaviors, accurate model of system dynamics is usually needed, but this can result in expensive computation. In this work, we explore whether we need accurate modeling over the entire look-ahead horizon for receding horizon planning of multi-contact motions. More specifically, we split the look-ahead horizon of the optimal control formulation into execution horizon and prediction horizon. The execution horizon covers the first step that will be executed in each planning cycle, while the prediction horizon considers the remaining steps which will not be executed. Although the execution horizon needs to be planned with an accurate model to ensure the motion for execution is dynamically consistent, we hypothesize that the prediction horizon can use simplified models to guide the decisions of the execution horizon, which can reduce the overall problem complexity. In particular, we focus on planning centroidal trajectories and we look for valid convex relaxations for the prediction horizon. This results in a novel type of formulation which we call receding horizon planning with multiple levels of model fidelity. Recently, a similar framework to ours is introduced for achieving model predictive control of 2D flat ground locomotion. In contrast, our work emphasizes on the receding horizon planning of centroidal trajectories for uneven terrain locomotion, where the selection of contact locations and timings are important to modulate the centroidal momenta. In this regard, the simplified model applied in the prediction horizon need to be carefully designed, as the quality of the model can significantly affect the performance of the framework. Next, we present the detail of our approach. In our work, the following assumptions are made. First, we focus on the bipedal walking gait, where a step motion consists of 3 contact phases: pre-swing, swing, and landing. This gives rise to a multi-phase formulation with phase-specific constraints. Second, we optimize contact locations and timings, while pre-specify the sequence of contact surfaces where the swing foot will land upon. Next, we describe the formulation of baseline, single-fidelity RHP, and 3 candidate multi-fidelity RHPs. For the baseline, we employ the centroidal model to plan over the entire look-ahead horizon, and we assume rectangular robot foot. For the first candidate, the execution horizon remains the same modeling with respect to the baseline, while the prediction horizon only considers the linear center of mass dynamics with rectangular foot assumption. Further, the contact timings are fixed. Comparing to the centroidal model, the dimensionality of the model used in the prediction horizon is reduced, and the original non-convex constraints are reduced to 6 convex ones. For the second candidate, the prediction horizon employs a convex relaxation which includes both the linear center of mass dynamics and a convex outer approximation of the angular momentum rate dynamics. For more detail of the convex approximation, we refer the audience to the selected literature. Same as the first candidate, the robot foot remains rectangular and the contact timings are fixed. Comparing to the baseline, the convex approximation employed in the prediction horizon has increased dimensionality and requires 48 convex constraints to replace the original non-convex ones. However, the model used in the prediction horizon is fully convex. For the third candidate, the prediction horizon considers the same convex relaxation of the second candidate, while switching the rectangular foot to single-point foot. This further reduces the dimensionality of the model used in the prediction horizon. To evaluate our approach, we use the baseline and three candidates to plan offline centroidal trajectories of the humanoid robot Talos in the scenarios shown in this slide. We validate the planned trajectories by tracking them with a whole-body inverse dynamics controller in simulation. For all the scenarios, candidate 1 failed to converge after a few planning cycles no matter how many look-ahead steps are included in the prediction horizon. Next, we present our experimental results for baseline, candidate 2, and 3. For the up and downhill scenario, the baseline can generate trackable trajectories at the expense of large computation time. For candidate 2 and 3, the trajectories generated with one-step look-ahead in the prediction horizon tend to exhibit jerky movements in our simulation, which causes tracking failures. However, candidate 2 and 3 can successfully generate trackable trajectories with 2 steps look-ahead or more in the prediction horizon, while having smaller computation time than the baseline. Similar results are obtained in V-shaped terrain as well, where the baseline always succeeds. Candidate 2 and 3 with one-step look-ahead in the prediction horizon generate jerky motion or fail in our simulation. However, with 2 steps look-ahead or more in the prediction horizon, the trajectories planned by candidate 2 and 3 can be successfully tracked in our simulation. In addition, the computation time of candidate 3 is smaller than the fastest of baseline. Next, we present the results for Rubbles. The baseline succeeds, but with extensively large computation time. With one step look-ahead in the prediction horizon, candidate 2 and 3 cannot generate trajectories that can be tracked by our whole-body inverse dynamics controller. However, candidate 2 and 3 with 2 steps look-ahead in the prediction horizon generates trackable trajectories in a fraction of the computation time of the baseline. To highlight the computation benefit of our approach, we compare the average computation time of each framework. Under same look-ahead horizon length, candidate 2 is averagely 2.3 times faster than the baseline. This suggests that the convexification in the prediction horizon can improve the computation time, despite the model dimensionality is increased. Also, candidate 3 achieves further computational improvement which is 4.4 times faster. This is because of the candidate 3 assumes point foot in the prediction horizon, which further reduces the model dimensionality. It is worth to note that, although candidate 3 require longer look-ahead than the baseline to succeed in our simulation, the computation time is still averagely 2.4 times faster than the fastest baseline. We consider this computational improvement is significant, because it suggests the potential of using candidate 3 in an online fashion. More specifically, we compare the computation time of each planning cycle for both the baseline with one-step prediction horizon and candidate 3 with two-step prediction horizon, as well as the duration of the motion plan being executed in each cycle. We can observe that the computation time of the baseline is often larger than the duration of the motion for execution. In contrast, the computation time of candidate 3 is always smaller than the duration of the motion for execution. This suggests that candidate 3 has the potential to run online, because the motion plan of current planning cycle can be computed before the robot finishes the execution of the motion for current cycle. To conclude, in this work, we propose receding horizon planning with multiple levels of model fidelity, which combines an accurate non-convex model and a relaxed convex model. The proposed formulation features reduced problem complexity while ensures the motion for execution is dynamically consistent. Further, our investigation suggests that considering angular dynamics in the prediction horizon is important. Lastly, our multi-fidelity RHP achieves averagely 2.4 times faster computation speed than the fastest single-fidelity counterparts, and has the potential to use online, owing to its fast computation. For more evaluations and discussions of our approach, we refer the audience to the paper. Thank you for watching.